Hi there, third years. This is a lesson recording to go with your radiation topic that we're doing at the moment. Some of this will be revision. It will either be revision from first and second year, or it may even be revision from the first assignment you had to do, where you had to do some work on alpha, beta, and gamma radiation. So I want you to watch this lesson recording. If I write some stuff down here on my whiteboard, I'd like you to get that into your red jotter. I'll be talking a little bit as well, giving you some background information about radiation. If I don't write it down, all you need to do is listen, and you don't necessarily have to write it down. So first of all, and I'm writing it, so that means you need to copy it down, is revision, but I expect you to have a note of it, is I want to have a look at what's called the structure of the atom. Now, the atom is like a particle, but if we zoom in on the particle, then we find that it's not just a solid lump. We find that it's actually got a center called a nucleus, and the nucleus is full of things called protons and neutrons, and I'll just color in some of these. It doesn't really matter which one's which, but I've done 8, and this has got 8 neutrons and 8 protons. So this is something called the nucleus. And orbiting around, this is a little bit like the solar system, where the sun is in the center of our solar system. It's surrounded by planets that are going round and round and round. And the atom, a very simple idea of the atom is that we've got this nucleus and orbiting round and round and round the outside. And I'm just going to draw 4, and there's a reason for drawing 4 of them. And these go round and round in different sorts of orbits, a little bit like the planets going round and round in different orbits around the sun. So you'll need to make sure you copy that down. Now, this is completely not to scale. Now, what does that mean? To get it on my page, I've drawn the nucleus here in the middle, as being quite large, and I've got the electrons, which look like they're quite close in, and they're whizzing round and round quite close in. But it's a little bit like our solar system again. The planets are a huge distance away from the sun, and this is the same with the atom, as the electrons are orbiting a great long distance away from the nucleus. And to give you a comparison, if you took something like a golf ball and you took it out and put it on the school field, there's a golf ball at the end of the school field near the school, the first electron would be right up the end, at the other end of the school field. Now, you can't possibly draw that to shrink that in your book, so this isn't to scale either, but that would give you an idea of the field. And this is one end at the school and the road, and where the buses come in, and this is right up the very far end, as far away as you can get, and that's how far the electrons are. So if you think about that in terms of this diagram is not right at all, but the distance here is just full of empty space. So 99% of our atom is just empty space, if you can imagine these electrons whizzing round and round and round. So completely not to scale. Now, these particles that are orbiting and the particles in the middle, they have a property called charge. Now, what does property mean? It's a sort of description of what they are. And protons have what's called a positive charge, whatever that means. I'll come back to that in a minute. Electrons, which are whizzing around the outside, have a negative charge. P for positive. And lastly, our neutrons have no charge at all. And they're otherwise known as neutral. Can't spell. N-E-U, neutral charge. And the neutral bit is the same as neutrons. So what does this charge thing mean? Well, they can cancel each other out if you've got the same number. So what I've drawn here is I've got 4 electrons, that's 4 negative charges, and I've got 4 protons, that's 4 positive charges, and the 4 negatives and the 4 positives cancel each other out, and the neutrons don't affect anything called charge at all. So the overall charge of this atom is also neutral, but it's just the bits that go to make it up have these things called positive and negative charges. Now, a different way of writing a positive charge is to write a plus, and a different way of writing a negative charge is to write a negative sign. And neutral, you could just write as a 0. It's got no charge at all. Okay, so that's the first bit. And again, you'll need to be copying all this down. And this is sometimes a bit difficult whilst I'm actually talking. So what you probably need to do is pause the video when it gets to a suitable stage. Pause the video and do some copying down in your book. Now, I do know that if you're pausing a live streaming coming from somewhere in Google land, it's downloading and playing to your Chromebook. It's sometimes difficult to pause and rewind and go ahead again. And the best thing to do if you're having difficulties, all depends, I think, on your internet speed. If you're having difficulties, the thing to do would be to download this lesson first and get it saved on your Chromebook. And then when you replay it and it's not streaming and you've actually got it downloaded, it's much easier to pause and rewind and concentrate on bits that you want to do. So you don't have to try and write everything down at the same time as I'm doing it, because that's a little bit difficult to listen to me, watch what I'm doing, and do your own work all at the same time. So you might pause it now and say, right, I've listened to Mr. Forward, I can replay it. What were the important things? The important things is all written down there. The important things are written down there. And you need to make sure you get that down before you go on to the next bit. So we've got these electrons which are orbiting round and round and round, like the planets going around the sun. Now, in our solar system, we have something called gravity. And the gravity of the sun, if you will just go away from the atom a minute, but it's a useful idea to look at this. We've got the sun, which is quite big. This is a bit like the nucleus, and we've got a small planet over here. And the sun, if the Earth was not, if this is the Earth, if the Earth wasn't orbiting round and round and round, the gravity between the sun and the Earth would get pulled into the sun and we wouldn't exist. But the Earth's been out here for over 4 billion years, and the only reason it stays here and isn't sucked into the sun by gravity is because it's orbiting round and round and round. As long as you're going round and round and round, you can't get pulled in to the middle. Now, the nucleus and the electrons are a bit like that as well. So if we go back to our nucleus is made up of some protons, here they are again, and some neutrons. I'll color in the neutrons. I'll put 4 of them again. Now remember, the neutrons don't do anything. They have no charge, but there's 4 protons. So overall, the nucleus has what's called a positive charge. And our electrons are whizzing round and round, and there's 4 of them, and I'm going to put them just all over here at the moment, and each one is negative. Now normally you'd say, oh look, this positive and this negative, they attract each other, and the electrons ought to get pulled into the middle. But just like our solar system, they don't get pulled into the middle because they're orbiting round and round and round. But normally, if they were just stood still, supposing I had a proton here, positive proton, and one electron over here, and they were just stood still, this wasn't orbiting, then these two would attract and they'd go in and the charges would cancel each other out, and you'd end up with a proton and electron stuck together with no overall charge. So remember this about the charges cancelling each other out. And every atom that we've got in existence, this board here, the table I'm writing on, you, me, we're all made of atoms, and the atoms all have different numbers of protons and electrons and neutrons, and you can find out about the structure of different atoms by having a look in the periodic table. If you do chemistry, you'll probably be using the periodic table quite a bit. You would have seen the periodic table as well in first and second year, and surprisingly there is in physics a periodic table in the data sheet information that you get for physics, and all the different elements all have different numbers of protons and neutrons. So hydrogen, the first element, has one proton and one electron. Helium, the next one, has two protons and two electrons. Hydrogen, helium. Lithium is number 3. Lithium has 3 protons and 3 electrons, and they've got some neutrons as well, but the neutrons don't do anything because they've got no charge. And whatever you do when you look at these different atoms, hydrogen, helium, lithium, beryllium, boron, and so on, they have equal numbers of protons and electrons, and that means overall they cancel each other out in terms of charge, and they don't have an overall charge. The atom doesn't have an overall charge. Now, of course, we've already learnt in last week's work that if we've got an alpha particle that comes along, here's my simple atom here, and if I've got an alpha particle that comes along and it either smacks straight into that electron or passes nearby, because my alpha particle has 2 protons, so it's got 2 positive charges and it's on its own, it hasn't got any electrons. My alpha particle comes whizzing past here, and if it comes whizzing past, it's got such a strong positive charge, it overpowers this single negative charge, 2 positives here and 1 negative charge, and it can pull out the electron from my normally neutral atom, and that neutral atom then has lost an electron and has become ionized. Now, you would have seen this in one of the video clips that you would have watched last week, and it tells you all about atoms losing an electron. You should have written down a statement underneath your table that you did to say what ionization is. And ionization is just a radioactive particle, could be a beta coming along as well, but its beta's not so good, and gamma doesn't do it at all, is that the alpha comes whizzing past, it's got a big positive charge and it can take away one of these electrons. Beta doesn't do this so well because beta itself only has 1 negative charge, and as it comes along, a beta managing to do anything to one other beta, it's got to be fairly good at doing that to get it knocked out, and it's not, because it's quite a small, these are 2 small particles and they don't interact very well. And the gamma doesn't have a charge at all. It's a bit like a neutron. It doesn't have a charge at all, and so it can't affect these electrons that are orbiting, and it can't knock them out at all, really. And so gamma doesn't do much ionization. Now, we'll come on to ionization again later in this unit, because atoms that lose electrons, especially if they're atoms in your cells, in your body, those cells, if they lose an electron and become ionized, that cell can become damaged, and we'll talk about what the damage is to your health of this radiation later on. So just a little bit about charges. If I've got 2 negative charges, say I've got 2 electrons sitting next to each other, they both have a negative charge. Negative charges, 2 of them don't like each other, so they will repel each other. Two protons sitting next to each other have a positive charge each, and two positive charges don't like each other, and so they will also repel each other. And as I said earlier, normally a proton and an electron, which has a negative charge, normally they would like to get attracted towards each other, which they can do if they were just sitting there doing nothing. But because this electron's in orbit, it doesn't have any effect. But if they were sitting still near each other, then a positive charge and a negative charge would get attracted towards each other. So what we have is a little saying, is that like charges, like is two that are both alike, two that both are like charges repel, and unlike charges, and that's a positive and a negative, they will attract. Unlike charges, attract, providing they're just sitting still and they're not in orbit. Otherwise, our atoms would all collapse and we wouldn't be here 4.3 billion years later. Okay, so I'll move on again. Now, a little bit about radioactivity itself. Radioactivity. Now, what does radioactivity really mean? Radioactivity means that the nucleus of an atom will emit a particle, either an alpha or a beta or a gamma. So these alpha and beta gammas make up something called radiation. And as I just mentioned just a minute ago, if you have electrons knocked out of your atom by ionization, then that could lead to a cell in your body being damaged, and that's a problem. A damaged cell is not a good thing to have. So radiation generally is a bit dangerous. And you can get different types of cancers caused by radiation. It's just one way in which cancers are caused is by radiation. It can also be caused by things like smoking. Lung cancer, for instance, is caused quite often by people smoking. But you can get different types of cancers. So we will be doing some stuff about the dangers of radiation to living cells later on. So we really should stay away from radiation if we get the chance. But unfortunately, radiation occurs naturally in nature. And a lot of radiation is produced by different types of rocks. One of the most radioactive rocks that produces the most radiation is a rock called granite. Now, fortunately, on the Black Isle, we don't have too much granite, because on the Black Isle, we live mostly on sandstone, and sandstone has little or no radioactivity. Or little or no radiation comes from it. But granite produces a radioactive gas called radon. And this gas is radioactive and it produces alpha or beta or gamma radiation, excuse me, which can fly around, and you can't see where it is. It's invisible. You can't see it. You can't smell it, and you need special detectors. And we'll be doing some stuff about detectors later on. Now, a few years ago, I think it was about 7 years ago, Highland Council decided to do a survey in every school in Highland to see how much radiation there was in classrooms. And it all depends on how much granite rock you're built on. And surprisingly, when they did some detecting of the schools on the Black Isle, they found almost no radiation. So it's not a problem in our school classrooms. But there are some schools that are built on granite, and most of these schools are either down Loch Ness side Drumnadrochit and Kilcumin in Fort Augustus. Drumnadrochit is in Drumnadrochit, halfway down Loch Ness. Kilcumin is in Fort Augustus, which is the other end of Loch Ness. And also up the east coast, going up towards Wick, there are some schools that are built on this special type of granite. And the granite produces radon gas, and the radon gas makes radiation. And the detectors that the council put in detected slightly higher levels of radioactivity in these schools. And I'm going to put a link to a BBC article which talks about the radioactivity. Now, that radioactivity is very, very low level. It's not really that dangerous. But the radon gas is quite a heavy gas. And if it's produced in a school, the gas settles to the floor. So unless you spend all day long lying on the floor in your classroom, you're unlikely to come across any of this radon gas, and especially not in Fortrose, because there isn't any. But if you're in Drumnadrochit or Kilcumin or Helmsdale, somewhere up the east coast, then there might be slightly more gas at floor level. And so what the council have done is they've put ventilators, they've put holes in the wall, and the radon gas can go out. And it's not really a problem in the Highlands. It can be a problem in some places like Cornwall. And not only do buildings have to have ventilation at floor level, they also have to have fans, and that will extract the gas out. So a lot of this stuff is around us, and it's been around us for millions of years, ever since the Earth was formed, and it's really difficult to get away from it. So that's just one type. I thought I'd just give you a bit of a local flavor there. So radon gas in some buildings, it's not just school buildings, but any building that's built on granite, they would have to do a radioactivity check to make sure radioactivity is kept as low as possible. But in some places, radioactivity is much higher than in the Highlands. So places like Cornwall and Dartmoor, the granite is different, and much more radon gas is produced, and they definitely have to have these ventilation systems in houses and fans. But it's still pretty rare in Britain. Okay. I'll move on from that. We will be doing more about different sources of radioactivity and their dangers later on. Right, so production. Where is this radioactivity produced? And I don't mean where in the country, I mean which part of the atom. So production of radioactivity, this time not do I get more of it produced down Loch Ness, but production of radioactivity from the atom. Now, all of the three types of radioactivity, alpha, beta, and gamma, are all produced. They all come from the nucleus. Now, you've already done a table, and you should know what alpha is, and I'm going to go through some of this stuff atom by atom, or bits of radioactivity. Now, alpha is made up of 2 protons and 2 neutrons. So it's 4 particles, 1, 2, 3, 4. And 2 of them are neutrons and 2 of them are protons. And because the protons have a positive charge, we already know that that overall means it's got 2 positive charges in the middle. Now, where does an alpha particle come from? Well, it comes from a nucleus. A nucleus is made up of protons and neutrons, and the nucleus in some atoms is unstable. So the nucleus is unstable, and the nucleus wants to get rid of some stuff, and it can either do that by putting out some particles or putting out some energy. This is called emission or ejection. So it's quite simple. If you've got a big atom, lots and lots and lots and lots and lots of protons and neutrons, and I'll color some of them in, then the alpha particle can get shot out. And what that means is that the nucleus becomes a little bit more stable, because it was too unstable. It was too much like a huge big pile of bricks, and it was going to topple over. So it shoots out some alpha. It shoots out an alpha particle, which is made up of protons and neutrons. So that comes from the center of the atom. Now, beta also comes from the nucleus of the atom. And what is beta? Beta is a negative electron. But in the work that I've just done, and you've already got written down today, we know that electrons whiz around the outside. But a beta particle is not one of the orbiting electrons. It's an electron that's produced inside the nucleus. And you'll say, well, how's that? Because Mr. Ford's just told us that the nucleus is made of protons and neutrons. So how can you get an electron out of the nucleus? That doesn't make any sense. So we need to do a little bit more about this. So an electron also comes from the nucleus of this unstable atom. And what it is a neutron. And the neutron decays into a proton and an electron. And as we've said before, the proton has got a positive charge. It should be an and. A proton's got a positive charge, and the electron's got a negative charge, and the two charges balance each other out. So a neutron can, of its own free will, change or decay into a proton and an electron. Now the proton stays in the nucleus, and the electron is ejected or emitted at high speed. So our ejected electron comes flying out of the nucleus. You'll also see this. I'm going to stick up some simulations. They're a bit like PowerPoints, and you can't, but I am able to click through the simulation. These simulations only work on Windows PCs, and unfortunately I can't get the simulations installed on Chromebooks because they wouldn't even work. So what I've done is I have taken some of these simulations and I'm running them on my home PC. I've got the installation rights to put them on my home PC, and then I'm clicking through the simulations, and you can see these simulations as if you had them on your own computer. Now you can't click on them. I've seen people try and do this before.
Sorry, I don't know that one.
Apologize about that. That was my little Amazon device there, whose name happens to be computer, and it suddenly switches on and starts to listen to me. So every time I mention the word computer, it goes a bit bonkers and plays a message. Computer, stop. That will turn it off, hopefully. Right, so I'm going to call it PC now. So I've recorded these PowerPoints type animations on my home PC, and you can't click on anything to get it to work. So you just have to sit back and watch it, and I advance through the slides and you get little simulations, and you'll see some of these simulations, alpha, beta and gamma, on the Flash physics files that are at the end. They're linked outside of the video here. So that's beta. It's an electron, not an orbiting electron, an electron that is ejected, having been made by a neutron decaying. Right, lastly, gamma. Now, gamma is not a particle. Unlike alpha and beta, gamma is not a particle. What is it? It is a burst of electromagnetic radiation. And we've done loads already about electromagnetic waves. So a gamma thing is a little wave of energy that comes out of the nucleus. And it's just like all the other types of radiation in the electromagnetic spectrum, but it's right at the top end of the spectrum. And as you go through from radio and you move up through infrared and visible and so on, and you get right to the very end, once you get past ultraviolet, the types of radiation have much more energy. And because gamma is right at the top, you've got ultraviolet, got a little bit of energy. It's dangerous enough to give you skin cancer. If you get overexposed to sun, you get sunburn and you can get your cells get damaged. X-rays definitely can damage cells. And if you go to hospital, they will check up and see how many X-rays you've had. And if you've had too many X-rays already, they won't give you another X-ray, and you have to have another type of scan. And gamma is even further up, so it's got even more energy and it's more dangerous. So it's a burst of energy, and because it's not a particle, it doesn't take away particles from the nucleus. All it does is takes away energy from the nucleus because it's an energy burst, and it allows the nucleus to settle down. So you can have your nucleus settling down in two different ways. I'll just write down that it's an energy burst. So the two different ways is that particles are ejected, and that means it's less unstable. And what are the particles? They are alpha and beta, or energy is ejected, and that's your gamma radiation. And again, losing energy helps to make the unstable nucleus a little bit more stable, and it allows it to settle down a little bit. Right, now that's all I'm going to do at the moment. I'm going to stop this video, but I do want you to go and have a look at the other presentations. I wanted to get the other presentations ready for you before you did last week's work on alpha, beta, and gamma, but unfortunately I wasn't in a position to record them last week, but they're now recorded and they're now stuck at the end. You'll see a link and you'll be able to watch those. So there'll be details of your assignment for this week. Now, what is your assignment? Your assignment is to make sure you get these notes written up in your jotter. Your assignment is to watch the videos. Now, I have no evidence that you're going to watch the videos at all, watch this video or watch the other ones that I'm going to post up, but I do want you to watch them. And the proof that you've watched them and you've done something is that you have made some notes in your red jotter. Well, how do I know that you've made some notes in your red jotter? What I want you to do is to take some photos with your phone of the pages of work that you've done, and I want you to post the photos in a Google document. And then I will be able to see what you've done. Now, you should be used to doing that because I asked you to do a table last time, and I asked you to take a photo, and I asked you to put that in a Google document. I just want to emphasize some good things to do when you post some photos is the photos should be bright. In other words, they should have some correct illumination. What does that mean? That means that you need to have some lighting that shows up the work in your book. They want to have no shadows. It's very difficult for me to read what you've done if you've got your light, and I've got a light here at the side of my table. If you get in the way of the light, you'll get shadows all over your work, and then you can't actually see what's going on. So try and avoid shadows. They need to be the correct way up. There's no point in taking a photo and putting your photo in your Google document. So that's called correct orientation. It means that I can't read it properly because it's all written sideways. So you must make sure they're the correct way round. They're up and down and not side to side. And your writing needs to be nice and legible. If I get work in that's not bright and you've got shadows all over it, it's not the right way round, then I'll just have to send it back to you and say you need to fix this because I can't see it and I can't make suggestions unless you look after these things. So please try and do this before you submit your work. And that's about it for now. I'm going to stop this recording.